Hi everybody. Today we are going to be talking about the position time graphs, and this is another one that we already have a video about from Matthew, so please refer to that video. It's a little bit more detailed than this quick video, but I do want to kind of get us caught up in the booklet as well, just in case you're a perfectionist, you're a completionist, and you want to have all those pages of the booklet done. So it would be useful to have a method for illustrating how an object's position changes over time. The quickest way to observe patterns of movement, or this would be a quick way to observe patterns of movement, or to monitor the velocity of an object. One effective illustration is the position time graph. You are probably familiar with with constructing graphs from your studies in mathematics. Maybe, maybe not. And on a position time graph, time is monitored on the x-axis, while the position is monitored on the y-axis. So x-axis is here, this is x, and this is y. And we almost always will place time down here and then position on the vertical axis. And so what this means is that if it is an hour, if it has been 1 hour, then any position change in that 1 hour will be noted. So here's 1 hour. Any position change will be noted vertically, and here you can see that there is a small position change from 0, away from 0 to some value that wasn't quite 0. And then at hour 2, we can see that the position has changed again. Now it is almost 5 kilometers, so notice this is 10 kilometers on this line. This line is just a little bit short of 5. That would make this line here, the one that's on the y-axis, these are going to be in equal intervals, so that'll be 15, 20, 25. And we can see that these positions have been drawn out for us. We are seeing a steady increase in the position over this time. So I always think about it like time is moving constantly, so this is kind of, we're always traveling along this line, and then you're looking up to see what has happened at this time. So at each of these times you can see that we have been moved a little bit farther away than where we started, and always referring to where we started in this case. So you can see that the amount of movement away has been increasing. And in this way we can kind of treat them as almost two separate number lines, but then they're overlaid into a two-dimensional grid. Once you place your coordinates on the position time graph, you can join them with a line. The shape of the line on a position time graph, be it straight, curved, or horizontal, can tell you a lot about the velocity you're measuring. So in this case, we would say that if we started at 0, 0, assuming that we started 0, 0, we can see that a line would be sort of a curve. And that curve is always interesting because it looks like that the jumps are getting larger and larger every time. Notice there's only a little jump here between these 2 points, a little bit bigger, a little bit bigger, a little bit bigger, a little bit bigger, a little bit bigger. So it's almost as if the amount of distance being covered in an hour is increasing, or the velocity is increasing. So for each of those sets of variables, find the missing information and fill in the blank spaces in the table, using a plus sign to indicate forward movement, a minus sign to indicate backward movement. So here we have a change in position, the velocity of an object in motion. So the change in position is 20 centimeters, and the change in time is 5 seconds. So that would be 20 over 5, 20 centimeters over 5 seconds. So that gives us 4 centimeters per second. I feel like this should have been in the previous book. That's okay. All right, this is 52. This is the average velocity, right? So this is velocity. And for this one, we're using this average velocity formula. And we're missing our hats again, but that's okay. And now with the average velocity, if you're in a case where you're missing the position, the change in position, this is our delta, our change in position, or change in d, and this is our change in t, and this is our velocity. If we are missing the change in d, there are a couple of options here. One option is to learn the inversions of this equation. So for example, for this equation that we wrote out this way, what you can do is you can take this equation, duplicate it. Oops. I just also realized that I didn't put my hat on there. Okay, so we're going to take this equation, duplicate it, and what you can do is you can move things around. Like you can move the delta t up beside the velocity like this as a multiplication, as long as you change the variable's position there. Also, you can even do a complete swap of two of the values like this and do a complete swap, and that's also allowed by mathematics. So mathematically, if something is being divided on one side, you can equivocally do the multiplication of that divisor on the opposite side of the equal sign. And there's some reasons for that. I'm sure if you go deeper into your math, then you'll know why that is. Comes from algebraic notion. So in this case, if we are looking for delta d, the displacement change, then we are actually looking for the displacement change, and we need an equation that has the other two values on the same side. So we are going to take this 52 centimeters per second, and we're going to multiply that by the 13 seconds, and that's going to give us the value for the displacement. So let's just do that here, 52 times 13, and we get 676, and that would be the centimeters. Another piece of evidence that you're doing this right is that the seconds will cancel out. If you need to find the t, then you're going to take your displacement and you're going to divide it by the velocity. So that means we're going to take the 50 centimeters divided by the 5 centimeters per second, and that gives you 10 seconds. And again, you're going to see some canceling happening here. The centimeters are canceled out, and if you divide by a number that's in the denominator, then it becomes in the numerator, or a value in the denominator. Okay, so the last one, we have second last one, we have a negative 120 centimeters divided by 10 seconds. And so that gives us negative 12 centimeters per second. And the final question is we're going to multiply the negative 3 centimeters per second by the 75 seconds, canceling out the seconds, and getting negative 3 times 75, negative 225 centimeters. Quite a little bit of traveling. Okay. The second question we have here is a question about a ladybug moving around. So this is a distance and displacement question. So let's play around with that. So here we have we want to see what is the distance between A and B. So assuming that A here is at 0, this is going to be 0, 0, and E will be at the end, which we're going to assume is 100. Okay. So the distance from A to B in terms of distance would be simply 30. We can just count it. The displacement is going to be, we're going to take the 30 centimeters to the east minus 0 centimeters, and that gives us 30 centimeters east. So the movement is to the east, and the movement is east. Remind myself. Okay. From C to B, we would be traveling simply one movement of 10. Why did I say centimeters? Oh, it is in centimeters. Okay, so this would be 10 centimeters. But in the displacement case, we would be moving 10 centimeters to the left, or starting at 40 centimeters east, or that's our starting point. So actually, we want to do that last. We want to always do end minus start, so we want to do 30 centimeters east minus 40 centimeters east, which gives us negative, which gives us, yeah, I guess we'll call that negative 10 centimeters east. So that's fine. We can call that negative 10. Or maybe, you know what, let's get rid of the east and west in this calculation, and we'll just look at the bulk movement later. So we can just call that positive. We'll call this first one just positive. That'll be our we do need a direction, right? So we're going to use positive here. So positive 30 minus 40 centimeters, and that equals negative 10 centimeters. And so that movement, that negative movement, indicates that we are moving in a westward direction. All right, from C to D, we are going to be going from 40 to 60. So we can just say 60 minus 40. And that gives us 20 centimeters. That's fine. And we can do the same calculation for displacement in this case because the direction is all in the same direction. So our final position is at D, which is positive 60, minus C, which is also positive 60, but we still have to take the negative, or take the subtraction. And that gives us a total movement of plus 20. Now in this case, because it's a displacement, we do need a direction, so that's why I'm including the plus. And that indicates that the total direction of movement is to the east. All right, so if we go from C to E and then to D, then we are talking about from C to E, which is 100 minus 40. That gives us 60 centimeters for C to E. And then we're going to add that to from E to D. So E to D is 100 minus 60. We're just trying to find the magnitude in the distance calculation. So I don't actually care which number is first. I just want the number to always be positive. So that's another 40 centimeters. And that gives me a total of 100 centimeters by distance. You're free to count this one if you wanted. You could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's my distance traveled. And for my displacement, I can think about the final position, which is at D, right? So the final position is D, 60 centimeters. That's my end, right? And I'm going to take away my beginning, which was 40. And that's start. And so that gives me a total of positive 20 centimeters. And so that is still a easterly movement. Okay. All right, so that was a weird diversion in this booklet. I'm going to move that up next year and switch those pages. So introducing the introduction to graphing velocity. So this is what we really wanted to talk about. And so up to this point, we've studied velocity as a definition and as a mathematical equation. However, there are more ways we can communicate this information, such as constructing a graph. So as you know, there are two axes on a graph, the x and the y axis, and the slope of the line is the steepness. And slope is indicated as rise divided by run is equal to slope. Or the change in x, the change in rise, which is the change in y, divided by the change in x is also slope. Which also means that y2 minus y1 divided by x2 minus x1 is equal to slope. Okay. So the change in the y-axis is called the rise in the graph. The change in the x-axis is called the run of the graph, which means that for a position time graph, this would be delta d over delta t. That's a little interesting because isn't the change in velocity also delta d over delta t, right? And we do get a direction in these graphs, so let's keep those directions, arrows. So the slope of a PT graph gives the velocity of an object. And remember that slope is the steepness of a line. So the steeper the line of a PT graph, this is really the key point to take away today is that the steepness of the line of a PT graph, the greater the velocity will be for that time interval, or that instant of time. So if I simply draw out a graph and I say, hey, it looks like this, and this is D, and this is T, and if you said like, hey, this is runner 1, and this is runner 2, which one is the faster runner? Well, this is a steeper line, so this is a faster runner. Faster. And this is slower. And what about if we drew someone who was like this, completely horizontal? Well, they have no speed. Okay. And if it was straight up and down, then it'd be like infinite speed. So velocity is speed with direction. This is what we're going to get out of here. So here are some examples of some position time graphs. All the time intervals are equal for the time between the positions of the car. So no movement. What is this supposed to be? Well, I don't know what this is. I don't like this thing. Let's just get rid of that. Blech. What an ugly graph. Okay, so let's look at this graph here. So here we have a graph of this is what they're trying to get at. If we had an object that is not moving, then its position stays at the same place for the whole time. I guess what they're trying to say is that maybe we can look at this graph. Imagine this car is sitting here and it's not moving. Then for every time interval, whenever we look at this car, we keep looking at it over multiple times, it's always in the same place. So it's always the same distance from the distance along the position line of the graph. And that means that the car has a slope of 0. It has no change in position over a change in time. So we do have a change in time here. This is the time, right? This is a change in time. But this direction, we have the change in displacement is equal to 0. So the slope is 0. Now you could also have this written this way. If we wanted to calculate the velocity now, then the velocity at any one of these times is also 0. And we'll talk about that one soon. All right, so here's this so soon that we're going to do it on the next page. So the introduction to velocity, time, and accelerated motion. It is quite rare that an object moves in a uniform motion for any length of time. Think about riding your bicycle at what you consider to be a constant speed. Every time you turn a corner or go over a speed bump, you're speeding down, up, or slowing down. This means that you are accelerating, which automatically means you are no longer using uniform motion. In this lesson, we will analyze objects that change their velocity and learn how to track accelerated motion. So this is called understanding accelerated motion. The equation for velocity you have used so far measures an object's average velocity, the displacement during an interval of time. You should remember that from earlier lessons that displacement does not always reflect the total distance you have traveled. The average velocity equation will give you a completely accurate reading when an object is in uniform motion, but when an object speeds up or slows down on an interval on its time travels, this becomes an estimate of the current velocity. So here's a picture of someone traveling from Winnipeg to Grand Beach. You can see the time that it takes them and the distance or the displacement in terms of kilometers. So this is kilometers essentially north, right? We're going to say towards Grand Beach is the direction we're moving. So we can see two distinct slopes here. We can see slope number 1, where right here, let's say, between Winnipeg and Selkirk. And so with this slope, what we can see is that the change in time is 25. The change in time here is equal to 25 minutes. And the change in displacement is equal to 40 kilometers. I guess this is a distance. It doesn't tell us what direction it's moving. So let's just assume it's distance. So which makes this actually speed. But anyways, doesn't matter. There's a landmark, so I guess we can give it. All right, they have to make it. They've got to figure this part out, whether they want to be specific enough that they can include the arrows or not. So let's just call this towards, away from Winnipeg, right? It's away from Winnipeg. So it does have a direction. Okay, so in this case, the slope here would be 40 over 25. 40 divided by 25, which means you could multiply by 4 and divide by 100. And that would give you your kilometers, I believe. So that would be 160 divided by 100, which seems low. Let's see. So they went 40 kilometers divided by 25 minutes. Oh, because it's in minutes. Yeah, so it's 1 point. So this gives us 1.6 kilometers per minute, which is not a particularly useful measurement. And then you can see in the second half of their travels, I'm just going to make it straight so I can kind of see where we're at. You can see that they travel an additional 60 kilometers because they go from 40 to 100, and they travel for an additional 95 minus 25, the additional 70 minutes. So that means that we have a slope equals 60 kilometers divided by 70 minutes, or this slope is also their velocity. And so 60 divided by 70 minutes, and you've got a 0.86 kilometers per minute. And so that's a really peculiar thing, and honestly, in this case, because why did they slow down, right? So this is slower. Maybe they got a flat tire or something, but this section is slower, and this section is faster. And now what you can also do is, if you really want, you could have also looked for the average velocity here. And I'm going a little bit off the book here, but that's okay. And in the average velocity, we would see that the total distance is 100 kilometers. And the total time is 95 minutes. And so the slope here, I'm going to just do it over here, is going to be the 100 kilometers divided by 95 minutes to give us a new speed, a new velocity of 1.05 kilometers per minute. And that tells you something. It tells you that, if you want the average speed, you'll get somewhere in between the two numbers you had. So we had 1.6 for one and 8.6 for the other. So we end up with a number for the average, which is this red triangle we drew, and that average is 1.05. So this is an example where if I just calculated the average, I wouldn't get the whole story. We get more of the story when we start to break apart our trip into multiple sections. And so there's our example. They do the calculation as well. Now you could convert up to to a time in hours, and that would require us to multiply the minutes away by multiplying by 60 minutes over 1 hour. And that would give us our average velocity equal to 63 kilometers per hour. And here's another example where they got 52 kilometers per hour for that Selkirk to Grand Beach trip. I don't know why they're going so slow. I'm pretty sure it's 100 kilometers per hour on that section of road, but maybe I'm mistaken. All right, so here's a little activity we can do. We have we're going to calculate the velocities at the speed intervals specified on this chart. So here we have a whole bunch of values here. You can see that it ranges from 20 meters away to 80 meters away over a time of 20 seconds. So the average velocity from 0 to 5 seconds, that would be this first little triangle here. And so that would be a change in position of 10 meters and a change in time of 10 seconds. So 10 meters divided by 10 seconds gives us 1 meter per second. To go from 10 to 15 seconds, we can see that these two, oops, didn't want to draw a straight line. Okay, another increase of 10 meters and another increase of 10 seconds. So this would be 10 meters over 10 seconds. And so that gives us another 1 meter per second. But if we go from 15 to 20 seconds, we can see the change here is we ended at 80 meters away and we started at 50 meters away. So that gives us a total of 30 meters moved, but we still have only moved 10 seconds. So 30 meters over 10 seconds gives us 3 meters per second. And the whole trip, starting in a different color here, from here to here, and all the way from here to here, we are going from 20 seconds. Oh, are they 5 seconds piece? Oh boy. Well, we'll go back in a second. 20 seconds minus 0 seconds. So that gives us a total of 20 seconds. And a total of from 20 to 80. So 80 minus 20 gives us 60 meters. So it's 60 meters divided by 20 seconds. And that gives us 30 meters per second. And I realize that these are all 5 seconds, and I'm a bad calculator here. Okay, so let's put that in. So this is 5 seconds, right? Is that what I said? Yeah, 5 seconds. Yeah, of course, 5 seconds. I don't know where I got 10. And so that means that this is 2 meters per second, and this one is another 2 meters per second. Right. 10 divided by 5. Now I just don't trust my brain. And then 30 divided by 5 should be 6 meters per second. And so now we can see that the whole trip has a value that's somewhere between the smallest numbers and the largest numbers, which is kind of what to be expected, I guess. Okay. In some cases, you might be interested in something called the instantaneous velocity. And so the instantaneous velocity would be the value at an instant as opposed to the value at an interval of time. So if you kept looking at smaller and smaller intervals of time, you eventually could find an instantaneous velocity, the velocity of an object at a specific instant of time. When the slope of a position time graph is constantly changing, instantaneous velocity readings provide far more accurate measurement of velocity. To find out how to measure the instantaneous velocity, read pages 16 and 17 of the In Motion booklet. Well, I don't think that's true in this booklet, so we're going to have to cross that out. Measuring them is actually incredibly challenging. Okay, so looking at the accelerated motion, in accelerated motion, objects are speeding up or slowing down, therefore the velocity is not constant. Since the slope of the PT graph gives the velocity, a changing velocity will mean that the slope of the PT graph must also be changing. And a line with a changing slope is a curve. The slope of a curve is at a given moment will calculate the velocity at that instant, or the instantaneous velocity. But how do you calculate the slope of a curve? The way to do that is with what is known as a tangent. This is a straight line that intersects a single point of the right angles and is at right angles to the radius of that curve. So this is a curve here, and here is a tangent, and this tangent would be able to measure the instantaneous velocity at the single point that it touches on that curve. And this can be a really challenging concept, and I don't really think we'll play a lot with this, but it is something that we do a lot in future courses. So here's some more work on tangents. Here's a radius of a curve. And at the edge of that curve, you can see that they have drawn a line that passes through a single point. And using that single point, we now have a straight line. We now can draw a triangle. If you can draw a triangle, you can find a slope. So that's really the important concept there. And so we can see that the two tangents here of this curve, and we can see that this graph, if we drew a nice triangle here, like so, versus drawing a triangle for this graph, we can see that this triangle is a lower slope, so this is slower, and this one would be steeper, so it would be a faster. So if this was how the speed was going, you obviously can't have speed turning in on itself, but if the velocity was increasing, then this is the kind of curve we might kind of expect. So let's look at this example here. So here we have a car, and each picture of the car is supposed to be at a different time point, starting from the origin and moving towards the positive direction. And we notice that the space between the cars at each of the pictures we take, so imagine we had a camera and it's kind of taking pictures every second, then we notice the car is moving over to the right a little bit farther each time. So the slope at 0 seconds is going to be 0 meters per second. But then as the slope of the graph is becoming more positive, the farther in the positive direction as we move through time. So the velocity is increasing. So if we see a nice simple graph like this in the position time graph, where the graph is curving upwards, then in the velocity time graph, what we might notice is a straight line. The distance is it says accelerated motion, but actually, well, anyways, I don't want to get into this, into the definition, the quibbles here. But yeah, we do see that the motion is the amount of distance between the object over time is increasing. So every time interval, the space between these two cars is getting wider and wider, and we expect, the next one would be over here, next one might be over here, and so every time you take a picture of this car, if you're taking it at regular intervals, the car moves a farther distance from the last position you took a picture of. And so that's what's being drawn here in this picture, where it's increasing in speed. Now, if we calculated the velocity, we would actually find that the velocity stays the same through that whole time. The velocity is uniform. So we can say that a uniform velocity still creates a curved position time graph. Now, you could also move away from your original position. That could create a negative velocity. This does not mean that the object is slowing down. It just means that it's moving in the negative direction. And so here we have an example where its position is moving towards the origin, and as it moves towards the origin, the slope is actually increasing in magnitude, even though it's becoming more negative. So drawing our little tangents here, we can see, I guess I should use my zoom function because I'm getting some ugly tangents. So if we try to draw a tangent, a line that only touches the curve at one position, we can see there's our first one. Here's another one. I'm just going to move this one around. And in our last tangent here, we can see it's incredibly steep. So the velocity is still increasing, and so but it is in the negative direction. So we do see the velocity is increasing, right? Because the numbers go up, magnitude still increases. Magnitude is increasing in negative direction. And so position time graphs for uniform motion are straight line graphs. The slope of a position time graph gives the velocity. If the line is straight, the velocity is uniform over the time interval. In these cases, since the velocity is uniform, there is no acceleration. So it is also important to look at something like this, where the position and the time are changing regularly. This is a uniform motion. So the slope of a PT graph is positive with a low value, and the velocity has a low positive value. The speed is low and the direction is positive. The line is straight, so the velocity is constant. The object is moving away from the origin to the right. So here we have an object that's moving. It's moving at regular. Notice that each interval is exactly the same. So each interval is the same, so it's always moving the same amount, and so that means that the velocity is staying constant. But the position is changing. Remember, if there's no change in position, then the velocity will be 0. If there is a change in position, but that change in position is always the same amount for every time, then the velocity will be a slope of 0, but it will be not 0. So here, uniform motion gives a slope of 0 for velocity, but a non-zero value. And just the same, think about what would this look like if it was moving backwards. So if these cars were turned around in the other direction, we would still expect that the position is changing. The graph would now would be going this way, and this value would be in the negative because the velocity would be a steady negative value. So here's another example of the acceleration graph. So here is the space between the cars is increasing. So the slope of the position time graph is increasing. And then the velocity is increasing at a steady rate. So on these graphs, the slope of the line, so if the movement is accelerated, the graph of the position time graph is curved. On these graphs, the slope of the line still gives the velocity, but only the velocity at that instant. Since the slope of the curve on the position time graph is always changing, so too is the instantaneous velocity always changing from one instant to the next instant. In these cases, the velocity is non-uniform or changing. There is an acceleration. Acceleration occurs when an object speeds up or slows down while moving in a straight line path. Acceleration is the rate at which an object changes velocity over time. It is a vector quantity, meaning that the direction in which acceleration acts is important. So below we have a chart that shows the velocity of an object is changing with time. For each second, the velocity changes by 3 meters. The acceleration of the object is therefore 3 meters per second. A better way of writing per second is to write meters per second squared. The acceleration is a uniform acceleration. So average acceleration is equal to the change in velocity over the time interval. Or in this case, we write it out as A average is equal to the change in velocity over the change in time. And please ignore these terribly written typed out equations. Use this equation here. And so we can go on to perform some calculations. I believe you did some calculations with Matthew already, so I'm just going to try to go through these a little bit quicker. So a cyclist has an initial velocity of 10 meters per second at time 12 seconds. That's an interval. This is a instant. And then at 30 seconds. So this is instant 2. And at instant 2, it was 22. So this is another velocity. So we can think about this is velocity 2, this is time 2, this is time 1, and this is velocity 1. Let's see. I guess they're positive values, so that's still vectors. So think about it like this. Often you'll write something out with sort of a time graph, and we have at 12 seconds we were going 10 meters per second. And at 30 seconds, we were going 22 meters per second. So what is the change? So the change here is a change of 30 minus 12, which gives us 18 seconds. And the change in velocity is 12 meters per second. Pause it. So the acceleration average is equal to the change in velocity over the change in time. So that means that it is equal to 12 divided by 8, and that's 18. And so we're going to get our calculators, 12 divided by 18, and we're going to get 2/3 or 0.67 meters per second squared. So that will be our final value there. Okay, a cannonball is shot out of a cannon at 40 meters per second. So again, I want to have a little velocity chart and I want to have a time chart. And so I had a time at 0 seconds, it's shot out, and it's initially firing at 40 meters per second. And then 3 seconds later, it's only going 15 meters per second, some high winds or something against that cannonball. So what is the average acceleration for this cannonball? So we have a total change of 3 seconds, and we have a total change of, now in this case, we do have to think that this is the second time, right, minus the first. So we're going to do 15 minus 40. So we have to think that it's going to be a negative 25 meters per second. So our acceleration is going to be negative 25 meters per second divided by 3 seconds. And that's not going to help me. I need that calculator back. So negative 25 divided by 3, that gives us negative 8.3 meters per second squared. And that will be our final answer. Now, does that mean it's slowing up, slowing down, or speeding up? Well, in the terms of negative acceleration, when the acceleration is actually negative, that indicates that we have a slowdown. Yes. So I'm going to include a little statement here, actually. Negative acceleration indicates slowing down. Okay, so acceleration time graphs, just like the position and velocity, you can draw a graph to show the change in acceleration over time. So the acceleration time graphs are very similar to velocity time graphs. The further away from your line is from the x-axis, the greater the acceleration. If the direction of acceleration is positive, then your line is above the x-axis. If the direction of your acceleration is negative, then your line is below the x-axis. A horizontal line indicates a constant acceleration. Here a car is moving to the right, but the velocity is decreasing. The acceleration is opposite to the motion. So here the position is changing in a positive direction, right? But as the car gets farther away from its origin, so it's moving away from the origin, right? As the car moves farther away from the origin, the speed is slowing down. It's actually, and so the velocity is decreasing. That decrease in velocity, if we solved the sort of slope of this, the slope would give us the acceleration. So remember that the slope of these lines here, right, these slopes give us the velocity. The slope here is the value of acceleration here. So each slope gives the next graph. And we notice that this is a negative number, and it is a constant slope. This is a continuous, or this is a uniform slowdown in a way for that velocity. The sign of the acceleration gives a direction in which the acceleration acts. A positive acceleration acts to the right, a negative acceleration acts to the left. So that's another way of thinking about it, that if you want to think about it all in the same terms of direction, here in this graph, if we had a positive acceleration, we would expect the car to start going faster because in the right direction. It would be additive to the direction of motion. Here, the negative acceleration, this is the negative acceleration, is acting opposite to the motion of the car. And so that negative acceleration slows the car down and decreases the space between every car picture. A positive acceleration does not always mean that the object is speeding up. Sometimes an object with a positive acceleration is slowing down. To make sense of the sign of acceleration, whether an object is speeding up or slowing down, you must also consider the sign of the velocity. So here's some summaries. A positive sign for velocity and a positive sign of acceleration would be speeding up and moving to the right. A positive sign for velocity with a negative acceleration means moving to the right and slowing down. So here they are opposite, so we get slow down. If the signs are the same, but they are both negative, then that means that you are moving in the left direction and speeding up. They are additive properties in this case. The acceleration is in the same direction as motion. If the direction of motion is negative, but the acceleration is to the positive direction, then that means that the direction of moving is left, but it would be slowing down because they are in opposites. So opposite signs mean that the object will slow down. Same signs will mean that the object will speed up for acceleration and velocity. When an object is in accelerated motion, it can speed up or slow down as it travels. This means that finding the average velocity of a long trip may give you very different results when compared with the instantaneous velocity during a short period of time. Finding the acceleration of a moving object will help you to understand just how quickly or slowly an object is changing its velocity. And with that, we are pretty much caught up to the motion section, or the forces section, and the laws of motion. So we'll continue in that section in the following weeks.